Welcome to the deep dive. We are constantly seeing incredible progress with large language models.
Absolutely. Models built on that transformer architecture, they're everywhere.
They really are. Performance is staggering sometimes.
Yeah.
But all that success, it comes with this huge efficiency problem.
You mean the cost?
Exactly. We're talking incredibly high training costs, massive energy use, and these bottlenecks, right? They make processing really long documents super slow and memory hungry.
Yeah, it's that scaling law paradox, isn't it? For years, it was all about bigger is better.
Right.
But the bigger they get, the worse those fundamental mathematical inefficiencies become, especially for long sequences.
Long sequences,
Yeah.
like summarizing a whole book or analyzing tons of financial data.
Precisely. The kind of stuff that's really valuable, but currently very hard to do efficiently.
Okay, so our mission today is to look at something, well, pretty radical. A departure from just scaling up. Instead of just throwing more compute at it, the researchers we're looking at today turn to the ultimate efficient processor,
The human brain.
the human brain. We're diving deep into a new family of models called SpikingBrain. The whole idea is to rewrite the efficiency rules for LLMs.
Yeah, this is really about using biology to drive engineering breakthroughs.
Okay.
We're looking at how they engineered mechanisms inspired by the brain,
Yeah.
from the big picture architecture down to the tiny details of the neurons.
To solve that scaling problem, the transformer's quadratic scaling.
Exactly. And the results they got are, well, pretty astounding.
How astounding.
We're talking demonstrations of over 100x speed up in time to first token
Wow, one of X.
for very long sequences. And importantly, they validated this on large computing clusters outside the usual hardware ecosystem, non-NVIDIA.
Okay, that 100x speedup definitely gets your attention. Let's unpack this. We should probably start where the trouble begins, right?
Yeah.
The transformer bottleneck.
Makes sense.
What are the specific efficiency problems they're trying to fix here?
So it mostly boils down to the attention mechanism, how it works. First, you've got the training compute cost. It scales quadratically with the length of the sequence.
The knowing thing.
Exactly. So if you double the length of your text input,
The compute needed quadruples.
right, that's a massive barrier when you want to train on, say, really long documents or conversations.
So training costs just become astronomical for long stuff.
They do. And then there's the second big problem, inference. When you actually run the model,
Okay.
the key value cache, the bit that stores past context,
Yeah, the model's memory.
that grows linearly with sequence length. So linear sounds better than quadratic, but
But when you're talking about, 500,000 tokens,
Yeah.
that linear growth still swamps your GPU memory fast.
okay. So even linear becomes a bottleneck for truly long context.
It's the major architectural bottleneck for those tasks.
And the paper also mentions just the practical difficulty of training these huge models stably, efficiently, especially on non-NVIDIA gear, like the MEDX cluster they used. Precisely. That environment kind of pushed them towards this whole spiking brain philosophy,
Which is?
finding totally new architectures, new training methods that just inherently avoid that quadratic trap.
Okay. And they had a plan.
Yeah, a three-pronged strategy, all focused on efficiency.
Right. A clear strategy. Can you walk us through those three pillars?
Sure. First, model architecture. They moved away from standard softmax attention. They used linear and hybrid linear types instead and integrated these adaptive spiking neurons.
Okay, architecture first. Second.
Second, algorithmic optimizations. They built a really clever, efficient training pipeline. It lets them sort of convert existing LLMs into their new architecture. Very efficient.
Interesting. Conversion, not training from scratch. And third?
Third, system engineering, basically customizing their software frameworks specifically for that MEDX hardware to make sure large-scale training and deployment actually work smoothly.
Got it. Let's dig into pillar one then. The architecture, that big mathematical hurdle, the knowledge and the scaling.
Yeah.
How do you engineer attention to sidestep that, but still, let the model find the relevant context?
Right, that's the core challenge. They essentially replace the standard attention calculation.
Wow.
Standard softmax attention needs to compare every single token pair. That's where the quadratic cost comes from. SpikingBrain uses two main variants that have linear complexity.
Okay, tell us about the first one.
So the main one is called linear attention. What they do is they get rid of the softmax function.
Remove it.
Yeah, and they reframe attention as a state-based linear recurrence. Think of it like a running state that gets updated.
And what does that buy them mathematically? What does that transformation achieve?
Well, for training, it gets them down to $1 in amputation, linear, which is already a huge win.
Okay.
But here's the really revolutionary part. For inference, it requires constant memory.
Wait, constant, as in the memory use doesn't grow with the sequence length?
Exactly. That's the holy grail right there. Constant memory means your context window isn't really limited by the GPU memory anymore. Doesn't matter if it's 100 tokens or 4 million.
That's huge.
Yeah.
If the memory footprint stays flat, that long context barrier basically disappears.
Pretty much.
You mentioned the researchers connected this to biology. How does linear attention relate to the brain?
Yeah, they see it as kind of analogous to how human memory seems to work.
How so?
It relies on this compressed, continuously updated state, a bit like our working memory uses the current input plus a limited updated snapshot of the recent past. It behaves like a Markov process, sort of.
Interesting. Okay, so that's linear attention tackling the long-range dependency problem with constant memory. What's the second variant they use?
That's sliding window attention, or SWA. This one's conceptually simpler.
Okay.
It basically keeps a standard-ish attention mechanism, but limits its view. It only looks at a fixed local window of tokens nearby.
So it's good for local context.
Exactly. Captures nearby interactions efficiently. And crucially, it also gives you a Galler training complexity and Euler's inference memory.
Okay, so two different Eulerline memory approaches. Linear for long range,
Sure.
SWA for local. They must combine them, right? Since each probably has trade-offs?
Yes, absolutely. They use hybrid models to get the best of both worlds.
How do they combine them?
They built two main models described in the paper. SpikingBrain 7b is focused on extreme efficiency. It uses what they call interlayer sequential hybridization.
Meaning?
They just alternate layers, a linear attention layer, then an SWA layer, then linear, and so on. Keeps inference memory constant.
Okay, that's the 7B efficiency model. Then there was the huge one.
Right, the SpikingBrain 76b model. This one uses a mixture of experts, or MOE approach.
76 billion parameters? That sounds massive again. How does that not become a compute nightmare?
Well, that's the cleverness of MOE. It's another brain-inspired idea, modular specialization.
Like different parts of the brain doing different things.
Kind of. It drastically increases the model's total knowledge capacity, 76 billion parameters total, but keeps the actual computation needed low.
Yeah.
Because for any given input token, it only activates a small subset of those experts. In their case, only about 12 billion parameters get activated per token.
I see. So lots of stored knowledge, but only a fraction is used at any one time. Sparse activation.
Exactly. Sparsity at the macro, network level, it boosts capability without bloating the runtime cost. And they even figured out an efficient way to build it called upcycling.
Upcycling.
Yeah, they started with a smaller, dense model's weights and essentially replicated them to create the initial sparse experts. Saves a lot of training hassle.
Okay, that covers the big architectural picture, the skeleton. Now let's zoom way in, to the micro level,
And the neuron.
to the spiking part of SpikingBrain. What's happening there? How is it different from a standard artificial neuron?
Right, so this is where they really lean into the brain inspiration for efficiency. They move away from traditional kind of energy-hungry computations.
Like the standard neurons in deep learning.
Yeah, or even more complex biological models like Hodgkin-Huxley or even standard leaky integrate and fire neurons. Those often have things like decay factors, which can be tricky and inefficient to manage on GPUs.
So SpikingBrain simplifies things.
Massively simplifies, aiming for stability and hardware efficiency.
What's the key feature of their spiking neuron design then?
It's the adaptive threshold spiking neuron.
Okay.
They got rid of the decay factor entirely, simplifying the time dynamics. The absolute key innovation is that the neuron's firing threshold, the voltage it needs to reach to fire a spike, isn't fixed.
It's dynamic. It changes.
Yes, it shifts based on the neuron's own internal state, its membrane potential.
And what does having a dynamic threshold achieve? Why is that better?
It gives them control and stability. It stops the neuron getting stuck, firing constantly, being overexcited, or becoming totally silent and useless, being overquiescent.
Ah, so it keeps the neurons in a sweet spot.
Exactly. They call it maintaining a moderately active state. It manages spike generation optimally. And that optimal management is where the real efficiency comes from. It leads to sparsity.
Sparsity again. How sparse are we talking at this neuron level?
They actually measured the resulting activation sparsity. It was 69.15%.
Wow, nearly 70%.
Yeah. So almost 70% of the potential computations are just zeros, non-events. Nothing happens.
And that enables What kind of computation?
Event-driven computation. Instead of calculating everything all the time, you only compute when and where a spike actually occurs. That's potentially orders of magnitude more energy efficient, especially on the right hardware.
Okay, this all sounds phenomenal, like almost too good to be true on paper. Quadratic to linear scaling, constant memory, 70% sparsity.
Right.
I have to ask the critical question here. What's the catch? What do they sacrifice in terms of performance? Is this spiking brain model actually as, capable or accurate as the baseline transformer they compared against, like the Qwen 2.5 model?
That's absolutely the right question. Because, yeah, usually extreme efficiency like this comes with a massive drop in performance quality.
So did it.
Well, what the researchers found, and this is pretty crucial, is that by using that smart initialization, the conversion pipeline we mentioned.
Right, taking the knowledge from a pre-trained model.
Exactly. By doing that, they minimized the performance loss. They actually achieved competitive scores on benchmarks, even with all these efficiency gains.
Okay, let's talk more about that conversion pipeline then. How did it help them train efficiently, minimizing data needs?
So instead of starting from random weights, which takes a ton of data,
Yeah.
they used this idea of attention map correspondence, basically aligning the attention patterns between their architecture and the pre-trained Qwen 2.57b base model. This let them initialize their model's key parameters, QKV, with meaningful values right from the start.
They essentially transferred the learned knowledge over.
Pretty much, yeah. Converted it into the spiking brain format.
That must be a huge operational advantage. How much data did it actually save them during that continual pre-training phase?
Massive amounts. They reported needing only about 150 billion tokens for the continual pre-training.
Okay, 150 billion.
Right.
How does that compare?
For context, that's less than 2% of the data you typically need to train a similar-sized state-of-the-art LLM completely from scratch.
Wow, less than 2%. That's incredible.
And this whole process also proved that their architecture could be trained stably at large scale on those Medic XC550 GPUs. It wasn't just a theoretical exercise. They made it work on real, non-standard hardware.
Okay, stability check, efficiency check, competitive performance check. Let's get to the speed then, the inference speed. We teased that 100x number earlier.
Right, the headline result.
How do they measure this radical speed up? What metric did they use?
They focused heavily on time to first token, or TTFT.
Why TTFT?
Because it's a really crucial metric for user experience, right? How fast does the model start giving you an answer after you give it the prompt?
Makes sense. And it directly shows the benefit of that constant memory.
Exactly. The linear architecture shines here. So at a sequence length of 1 million tokens, which is already very long,
Yeah.
the Spiking Brain 7B model achieved a 26.5x speedup in TTFT compared to the Qwen 2.5 baseline transformer.
Okay, 26.5x is already a huge leap.
Right.
But how does that become over 100x? Where does that number come from?
Right. It comes from the scaling. Remember, Spiking Brain's inference memory is constant, over in dollars, but the traditional transformer's key value cache grows linearly. So as you push the sequence length even longer, the transformer gets slower and slower because of that memory pressure.
Well, Spiking Brain's performance stays relatively flat.
Exactly. Its performance curve is flat, or nearly flat, with respect to sequence length for TTFT. So they extrapolated based on this trend. They conservatively estimated the speedup would be over 100x when you push the context out to 4 million tokens.
Wow. Okay, so for you, the listener, that means maybe analyzing, I don't know, a multi-volume legal contract or a whole year of company emails, potentially getting the first response almost instantly without hitting that GPU memory wall.
That's the potential, yes.
Yeah.
It unlocks use cases that are just infeasible today.
And the versatility seems just as impressive. It's not just for giant data centers. They tested it on consumer hardware, too.
They did. They deployed a smaller 1 billion parameter Spiking Brain model onto a standard desktop Intel Core i5 CPU.
Just a regular CPU.
Yep. And because its memory overhead stays constant during decoding, even on a CPU, it showed huge gains. It achieved a 15.39x speedup over a comparable standard model, Llama 3.2-1b, at a sequence length of 256,000 tokens.
So the efficiency benefits translate even to edge devices like your laptop or maybe even phone in the future.
Absolutely. This isn't just a server-side play. It could enable powerful AI on devices you actually own.
Okay, and finally, let's loop back to energy savings. You mentioned the sparsity enables event-driven computation. If you pair this with hardware that's actually designed for that, what's the impact on power consumption?
Yeah. This is where it gets potentially game-changing. When you run those sparse spike trains, those 70% zeros on specialized asynchronous hardware.
Neuromorphic hardware.
Exactly. Hardware designed to only consume power when a spike event actually occurs. The estimated energy savings are dramatic.
How dramatic.
They estimate this sparse spiking approach could reduce energy consumption by 97.7% compared to standard FP16 floating point math.
97%.
Almost 98% reduction compared to the standard way. Even compared to more optimized INT8 integer math, it's still an estimated 85.2% reduction.
That's not just optimization, that's a different paradigm.
It really is. It's a fundamental shift from clock-driven processing compute everything all the time to event-driven processing only compute what's necessary when it's necessary, like the brain.
Incredible. So let's try to summarize this deep dive then. SpikingBrain seems to have successfully married these biological ideas, the event-driven spiking neurons, the modular MOE concept with advanced computer science, these hybrid linear attention architectures.
Yeah, and in doing so, they really did manage to break that fundamental quadratic scaling wall of the standard transformer.
And crucially, by proving it works, proving stable training and deployment on the MedX platform.
Right, the non-NVIDIA setup.
They've shown that this brain-inspired, highly efficient approach isn't just theory. It's a viable path forward, a large-scale technology roadmap that exists outside the, let's say, dominant compute ecosystem.
It really serves as a blueprint, I think, a reference for how things could evolve.
Which leads us to a final provocative thought, something for you, our listener, to consider. If LLM architecture can genuinely shift like this, moving from being mostly compute-driven and power-hungry to being highly energy-optimized, inspired by the brain, what does that mean for the future? What will the next generation of neuromorphic hardware actually look like?
And maybe even more critically, how will this kind of energy-optimized approach change where we deploy sophisticated AI?
Right. Will the most powerful AI systems of tomorrow still live only in massive data centers? Or could they become much more distributed, embedded all around us in our everyday world?